Hey guys, hope everybody's doing all right. What we're going to do today is wrap up our unit on chemical bonding, and we're going to talk about the effects of intermolecular forces on physical properties. I find this stuff really interesting because it allows us to look at intermolecular forces from the previous lesson and really gives us some meaning behind those, right? Like, because something has hydrogen bonding or London dispersion forces, like what does that really mean in terms of the properties of that substance? So this will be pretty short, and then we'll go over some practice problems towards the end. Okay. I want to quickly review the practice problem from the end of the last presentation, though, just to recap this, so you have an understanding of it for today. So you have a bunch of substances, right? It says arrange the following according to increasing melting point. All right. So when we talk about melting point, we're going from what to what? Well, we're going from a solid to a liquid, right? So in order to go from a solid to a liquid, we need to break some intermolecular forces. So, your solid has, all of its particles are very organized, right? Like this. They vibrate in place. There's not a ton of movement there. Okay, that's your solid. And then you're going to go to a liquid where these attractive forces between these particles, aren't as strong. So here's your liquid, they're more spread out. This is like, I don't know, the 5th day of school. We talked about some of this stuff. These are horrible particles, sorry. Okay, so we're going from solid to a liquid here. In order to go from a solid to a liquid, we have to break those intermolecular forces. So the easier it is to break those intermolecular forces, then the easier it's going to be for something to melt, right? If it's really difficult to break these, then obviously it's going to be harder to melt that substance. And it's going to stay in the solid state for a longer amount of time. So a melting point, we're going to look at it again today. We'll tie it in with boiling point, same idea. We want to look at the strength of the intermolecular forces that these things have. So I look at these, and I look at that first one, that is magnesium oxide. And the first thing I notice is that it starts with a metal, and then it has a nonmetal. So as soon as you have a metal and a nonmetal, I'm done thinking, and I know that that's ionic. Okay, ionic compounds, like ionic bonds, really strong. Okay, stronger than any of the intermolecular forces that we talked about in the previous lesson. Intermolecular forces are really associated with covalent molecules, which is what the rest of these things are. So I look at the rest of them. I have CO2. Now I know from experience, I know that CO2 is C double bond O with some lone pairs, and then double bond O with some lone pairs. I know it's nonpolar. That was one of our examples in the polarity lesson. So I know it's nonpolar. There's no hydrogen bonding or dipole-dipole then. So this has to be London dispersion forces only. So London dispersion forces. Same thing with oxygen. I know oxygen is O double bonded to O with some lone pairs on each oxygen. Obviously it's nonpolar, so there's no hydrogen bonding or dipole-dipole moment. So again, London dispersion forces. And then water is our main example for hydrogen bonding. You probably knew that from bio. So we have hydrogen bonding here. These are all the primary intermolecular forces, right? So like water has hydrogen bonding, dipole-dipole, and London dispersion, but the main one's hydrogen bonding. So which one of these is the strongest intermolecular force or strongest force? Well, it's going to be magnesium oxide, right? So that's going to have the highest melting point. So that is going to be, out of the 4 of them, that is going to be the one that's the highest melting point. Which one will have the next highest melting point? So you're looking at which one is the next strongest intermolecular force. Well, it's going to be water, right? So water has hydrogen bonding. That is stronger than, in general, stronger than dipole-dipole and London dispersion. So that is next. And the last 2 are London dispersion. So which one of these is the stronger intermolecular force? You may remember from the previous lesson that a stronger intermolecular force with London dispersion has to do with the number of electrons, which is tied in with the molar mass. So obviously CO2 has an extra carbon, compared to O2. So CO2 is more massive, has carbon in it, so it's 6 extra electrons compared to the oxygen here. So this is going to be the next highest melting point, and then oxygen will be the lowest. All right, so that brings us to one of the choices over here. But I just want to recap that really quick. Ionic is the strongest. We go into a couple more attractive forces in AP Chem, but this is all we worry about for right now. Hydrogen bonding is next, and then London dispersion with CO2 and O2. Makes sense, right? Magnesium oxide is a solid, water is a liquid, CO2 and O2 are what? Well, they're gases, right? So of course it's going to be harder to melt MgO than it is to melt O2 or CO2 because they're already melted and boiled already, you know what I mean? So anyway, that takes care of that. So there's our answer. Okay, the strength of the attraction between particles greatly affects the properties of a substance or solution. So one of them we'll look at is viscosity. I briefly touch on all of these with you guys here, but in AP Chem I talk about these a little bit more. We might do a lab or two with them when we talk about some more details that are involved here. But we'll get the basics under control today. Viscosity is, the easy definition is how thick something is, but the more official definition is the resistance to flow. So think about water versus syrup. All right, so syrup is thick, it's very viscous. Oil is viscous, water is not. Oil and syrup have a high viscosity, a high resistance to flow. You can do a viscosity race if you're that bored right now. You can take a whole bunch of household like food items, put them on a dish, put a blob of each one on the dish, and hold the dish up sideways, and they're going to run down the dish. The one that stays together the best is the most viscous. Usually that goes along with the higher intermolecular force. Like an oil has a lot of carbons. It's a big carbon chain, so the London dispersion force is really, really, really strong there. So it holds it all together a little bit better. It doesn't flow as easily. Whereas something like rubbing alcohol is really small. Even though it has a hydrogen bonding in it, it's not that strong of an intermolecular force compared to like the huge London dispersion force that oil might have. So the thicker something is, the more viscous something is. Usually the stronger the intermolecular forces and the thinner it is, then the weaker the intermolecular forces. Surface tension is another neat one to talk about. Here's an example of some water bug, and you can see that the water actually bends when his like legs are on it here. That all has to do with hydrogen bonding. Okay, so hydrogen bonding is obviously relatively strong, and it makes a nice little like layer on the top here. Okay, so you can see one water molecule, hydrogen bonded to another one, hydrogen bonded to another one. When you put a very light force on that, the hydrogen bonding kind of like stays together. It holds those molecules together, and it doesn't let you break through and break that surface tension of the water. If you take a paper clip and hold it sideways, you can and you gently put it on water with another paper clip, you could actually make a paper clip float. I do that demo in AP, and you can see the water actually bending. I'll usually get my document camera and zoom in. You can see that. Okay, so surface tension has to do with intermolecular forces. Melting and boiling point, I kind of addressed already with that warm-up question. So the higher the attractive forces, the higher the melting point or boiling point. So fructose, a type of sugar, really high boiling point here. Acetone, water, obviously lower boiling point. Fructose has definitely some dipole-dipole interactions there, and is a lot of London dispersion as well, okay? So the combination of London dispersion with dipole-dipole forces really gives that a good strong intermolecular force and a higher boiling point. Something like acetone or water, much smaller. Water is much smaller. And even though it has hydrogen bonding, because it's so tiny, the intermolecular forces of water don't equal that of something like a big sugar, like fructose would be. Okay? So the higher the boiling point or melting point, the stronger the intermolecular forces are going to be. Another one is cohesion and adhesion. Cohesion is when something is attracted to itself, and adhesion is when it is attracted to something else. You probably learned that in bio as well. So here's water on the left and a rubbing alcohol, I think, on the right, and it's on wax paper. Okay? The water is going to bead up very well on wax paper. The wax paper is nonpolar. The water is polar. There's no attraction there at all, right? So the water is not going to want to spread out on that. You know what I mean? So the water is going to want to get away from the wax paper as much as possible. Very, very bad adhesion there. And it's going to want to, be more together with itself. Very, very, very strong cohesion for this example. Again, wax paper, nonpolar. Here's rubbing alcohol, or a type of rubbing alcohol, which is still polar, but it has a little more London dispersion as well, a little more of a non-polar end. So it's not as polar as water is, okay? So it still beads up on here, right? It's still not going to spread out a lot on the wax paper, but since it's polar, but it's slightly a non-polar end as well, it'll spread out a little bit more. It's a little more attracted to the non-polar wax paper because of that slight non-polarness of one end of this. If I had a non-polar liquid like some oil, it would spread out very well on the wax paper. Okay, because the wax paper is nonpolar. So cohesion adhesion has a lot to do with that, and intermolecular forces. So stronger intermolecular forces, more cohesion here, and the weaker intermolecular forces, you had less cohesion here with the rubbing alcohol compared to the water. You can see that in a beading test. A couple more. Capillary action is really neat. If you have a leaky basement, you get some water in your basement, you see it going up the cinder blocks here. That's capillary action. Clothing, more of like the polyester type clothing, not so much, the cotton wicks up sweat as well, but some of the clothing that really moves that sweat away from your body and brings it to the surface so it can evaporate. It's all capillary action. So the fibers in the clothing, how they attract that sweat from your body, how they pull it away from your body and let it evaporate. I think that's pretty neat. So that's like some science and action there with the clothing that you buy. We talk about in AP that evaporation is a cooling process. So if you're running and you're sweating, obviously it like helps your forehead cool off or your body cool off. That's what that clothing does. So if it pulls the sweat away from your body, then it evaporates, helps cool you off while you're being active. Paper towel, perfect example of capillary action. I always joke that the capillary action of the paper towels at school is horrible, right? You have like the smallest spill and you need half the roll of paper towels to clean it up. So that is poor capillary action with the paper towels we have at school compared to maybe some of the name brand ones you might have in your house. I don't know. Okay, that takes care of it. So what I want you guys to do is, this is just some practical application of intermolecular forces, but it's important to identify which intermolecular forces are in various things. So what you're going to do is do page 30 and 31, and you're going to answer those questions, and you're going to put some of your answers in Edpuzzle, and we'll see how we do. I'll go over it with you once you put in a couple of your answers and see how we did, and we'll just kind of take things from there. Okay, so work on 30, 31, then we'll go over it. All right, guys, for this first question, you want to predict the molecular shape for each of the following. So you should do a quick Lewis structure, and then you want to find out what your number of bonded and non-bonded groups is on the central atom, and then determine the shape from there. So I'll give you a second to put your answers in if it asks you what to do there for some of these, and then we'll take a look at what they are. So here we go. H2S is bent. If you draw that correctly, you should have two bonded here, two non-bonded here. Two bonded, two non-bonded is bent geometry with a 105 bond angle. CCl4, carbons, your central atom there, 4 chlorines around it, so you have 4 bonded groups, 0 non-bonded groups, so you have tetrahedral. And I try to find a picture of it with it in the tetrahedral geometry there for you. That'll come into play a little bit later. SO2, best structure for SO2 as of now is something like this. So we have sulfur with a lone pair, 2 double bonds. Those are your 2 bonded groups, 1 non-bonded. So that is, again, bent geometry. It's not our bent geometry like we had here for H2S. This H2S bent geometry is 2 bonded, 2 non-bonded, 105 bond angle. Here we have 2 bonded, 1 non-bonded, around a 116 bond angle. That was one of them in the VSE PR theory lecture you guys watched. Okay, FBR, or BRF, whatever. You could say it's linear. There's really no shape, I guess, because there's only 2 atoms. There's no central atom here. But this is what that one would look like down there. And then PCl5 is very straightforward, standard trigonal bipyramidal. So you have 5 bonded groups, 0 non-bonded groups. And I found it where I drew it in the right geometry. So you have your axial chlorines here and here, and your 3 equatorials here. Okay, that takes care of number 1. So for number 2, you want to list all the types of IMFs that would occur in each of the following. When you get better at this, you do not need to even draw some of these, honestly, and waste your time with that. And I'll try to walk you through some of those hints right now so you can save some time on a test or quiz or next time you have to utilize these. So every single one of these, what intermolecular force does it have to have? Well, every single molecule has to have London dispersion forces. So that's easy, right? Every single one has to be London dispersion. So I'm going to put that there first. Now, the next question you ask yourself is, which ones are polar, right? If one of them is polar, then you know it at least has dipole-dipole interaction, and potentially hydrogen bonding. Okay. Keep in mind for hydrogen bonding, you need hydrogen. But first of all, it needs to be polar. Okay. Then it needs to be hydrogen bonded to N, O, or F. Okay. So hydrogen bonding is H connected with either N, O, or F. Those are the top 3 electronegativities on the periodic table, right? And it has to be polar. That's key, all right? If you have something that's non-polar with H connected to N, O, or F, it's not going to work, okay? So I'm going to go through these one by one here. I have CH3CF. I'm like, all right. I could draw how this looks, right? But I know one end of my molecule is going to be CH3, okay? I'm not going to have a lot of room to draw this. So I have carbon here and 3 hydrogens over here. And then it's attached to another carbon, right, with 3 fluorines. Well, as soon as I think about that, I'm like, okay, the 3 fluorines over here, very electronegative, right? Highest electronegativity on the periodic table. Over here, I have a bunch of CH bonds. Well, there's really nothing happening over there. So very electronegative end over here, as I wreck my lovely drawing. Very low, hardly any electronegativity over here. So it's definitely going to be polar with the electrons in this direction over here compared to that. Okay, so the CH3, CF3 is going to also include dipole-dipole. The CCl4, I'll put these up here now. The CCl4, I knew from the previous slide, CCl4 is tetrahedral, right? That's a very symmetrical shape, so even though I have dipole arrows going out, 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 they all cancel, right? So it's overall non-polar structure, so it's just going to be London dispersion. SO2 is going to be dipole-dipole. If you go back, sorry, I keep doing this, I should have designed this better, but I didn't. So here's SO2, there we go. So you can see that this would be partial negative, partial positive up here. So this is definitely going to be dipole-dipole interaction there. BRF, this is just ridiculous. Okay, BRF, over here, fluorine's more electronegative, right? So partial negative there, partial positive here. So dipole-dipole interaction there. And then I know PCl5 is there, okay? So PCl5, same thing. You have dipole arrows going out. I think if I look at the electronegativity difference the right way, there, and there. You know, the axial up and down cancel, and the trigonal planar equatorial all cancel out too. Okay, so you have everything canceling out there. So that's also nonpolar. I'm not sure if these dipole arrows belong here. I don't have my electronegativities handy right now. I think they do go there because Cl is pretty high. But anyway, that takes care of those. And now we have CH3, 3N. So this is you know, a little complicated here to take a look at this, but you have your nitrogen, okay, and then you have 3 CH3s, okay, CH3, you get the idea, CH3, CH3, and nitrogen will have a lone pair, it usually does, and nitrogen is very electronegative, right, so you're getting electrons pulled up, remember this is pyramidal, right, because of that lone pair on nitrogen, up, up, up. So up here, partial negative, negative, and here's your partial positive down here underneath. That's a mess, okay? So there's no hydrogen bonding for these because none of them have H connected to N, O, or F. Don't get mixed up and think like letter E has hydrogen bonding because you're like, oh, I see N's and H's. Well, that's easy. It doesn't work that way. You want to draw your Lewis structure, be familiar with that. You don't need to know a ton of this. Like, you don't need to be really, really fast at this right now. In AP Chem, you'll need to be fast at it. But we'll review it more and do it more then. It's easy for me to go through these because I know the shapes as soon as I take a look at them. The more practice you do, the faster you'll get at it. So you'll know, oh, CCl4 tetrahedral, not a problem. London dispersion only. You'll know PCl5. I can picture that. Trigonal bipyramidal, easy. But for right now, you might have to draw them out. It might take you a little more time. Oops. Okay. Number 3, to wrap try to wrap these up here. You have HBr, O2, and CH3OH. You want to represent the IMFs that are in each of those and the relative strength. So, go through and figure out what the IMFs are in each of these. Remember, all three have London dispersion. I think on the slide here, I only have the main IMF. So O2 should be easy by now. It's the same atom bonded to itself. So that is the most non-polar one here, and that's London dispersion only. HBr can't be hydrogen bonding because it's not H connected to N or F. So it's H connected to Br. So you want to look at your electronegativity differences there. Look at your periodic table of electronegativities. And you'll see that bromine, how that compares to hydrogen, and see what that electronegativity difference is. And then here's a hint for you. You have CH3OH. As soon as you see a hydroxyl group, usually dead giveaway for hydrogen bonding. Okay? So you have carbon, 3 hydrogens. That's your CH3. And then here's your OH right there. Okay? Lone pair on oxygen. Okay? This is going to give you a partial negative here. All right? And then your partial positive, over here somewhere. Okay? Definite hydrogen bonding because of this negative region right there, that OH. Okay? So here's the answer. Main IMF is dispersion, LDF for O2, dipole for HBr, that also has LDF, and then CH3OH. Here's a hint there, that OH group should be a dead giveaway to look for something like that. You'll have LDF, dipole, hydrogen bonding. So strongest to weakest. You can see 1 is the strongest, 3 is the weakest. For number 4, circle all the species that can form a hydrogen bond. So here again, you're looking for H connected to N or F and that substance being polar. So take a second and select the ones that can form a hydrogen bond here. We'll go over it. Okay, C2H6 is definitely out. Doesn't contain N or F. KCl is out. Doesn't contain N or F. It's ionic. And CH3, OCH3 is out. You need to know what that structure looks like a little bit. That'll be dipole, but it won't be hydrogen bonding because the carbons are connected to the hydrogen, and the hydrogens are not connected to oxygen. So again, the more you know about these, the more you do these, the more you realize how they look. So you're going to have oxygen here in the middle. You're going to have carbon, and those are your 3 hydrogens. Okay. Sometimes they write these kind of how they're written. You have CH3, so carbon connected to 3 H's, and then your O, and then connected to carbon with 3 H's, right? So those 3 H's connected to carbon, those 3 H's connected to carbon. It just makes the most sense that way. It can't be really written any other way. So that's out. So the only 2 that are hydrogen bonding are here. You have CH3, connected to nitrogen, connected to 2 hydrogens, a lone pair. Okay, so N connected to H right here. That gives you hydrogen bonding. And then here you go, OH group at the end. Easy money, okay? So you have a whole bunch of C's and H's of being a chain like this, kind of organic chemistry. Then you have your OH at the end. All right, very polar hydrogen bonding group there at the end, with more of a non-polar section over here. Talk about that in a different course. Okay, number 5. Rank the following compounds from weakest to strongest and to justify your answer. So we can take a second and do that and then take a look at it. Okay, so you take a look at these. Water, by now, is hydrogen bonding. Okay, I2 and N2 are London dispersion. Okay, because they can't be anything else, right? I bonded to itself is nonpolar. N bonded to itself is nonpolar. So London dispersion. And then H2S is not as, if it is slightly polar, it's definitely not hydrogen bonding. So hydrogen bonding is the strongest here. Okay, that's the strongest. I guess I can put a 4 there. I don't know. Here it is. Okay, H2S will be the next strongest. And then here are your 2 weakest, I2 and N2 for London dispersion. So what you want to do there is take a look at the size, okay? Nitrogen is really small, okay? So not a lot of electrons here to make those temporary dipoles for London dispersion. Iodine is humongous, right? It's in level 5. So iodine is definitely stronger, okay, than nitrogen is because it's bigger. So the tiebreaker, remember, for London dispersion is the larger it is, the more electrons it has. It's a fancy word we call polarizable. The more polarizable it is, the stronger the IMFs are going to be on that. Okay, so N2 is the weakest, then I2, then H2S, then H2O. Finally, I have the answer there already. Rank the following from weakest to strongest and to justify. So if you notice, you have H2SE, H2S, and then PO, and then TE. On your periodic table, they're all in the same column. You have S, you have SE, you have TE, and you have PO. All right? There's no hydrogen bonding for any of these, right? So it's either London dispersion or dipole-dipole. They're all relatively nonpolar, right? So, so that really means they're primarily London dispersion for all of these. It's the primary IMF. Since they have the same shape, they're all bent. They all have the same like main intermolecular force. The larger one is going to be the stronger intermolecular force there. Polonium's humongous. It's in level 6, right? It's huge. Okay, to take up this much space, a lot of electrons here to create temporary dipoles and give you a really, really strong London dispersion force. Sulfur is a lot smaller. It only take up like that much space. It's smaller, so it's not as much room for temporary dipoles. If you look at the halogen group, that makes sense. As you go down from fluorine, like F2, down to I2, you know, they're all nonpolar London dispersion, but fluorine is really small, so it's weaker IMFs, so it's in the gas state, and iodine is in the solid state, so I think that's really neat. Anyway, hope you understand some of this. It really takes care of Unit 9. We'll take a quiz soon, and we'll be, off to Unit 10. All right, guys, have a good day.